So for a diatomic molecule, the translational motion of the molecule as a whole is pretty much due to the motion of the two nuclei. You can pretty much ignore the electrons. Remember, when you're calculating the center of mass, there's hardly going to be any contribution from the electrons. Besides, electrons really move so fast that it's just a blur around the two nuclei, so the electrons would pretty much just follow your nuclei as it moves. Okay? Vibrational energy, okay, the internal motion and the rotational motion, that's for the molecule, that's pretty much keeping track of the movement of the two nuclei. Okay, so when we talk about translational energy, vibrational energy, and rotational energy of a molecule, we're talking about the movement of the nuclei. Now, when we get to apply quantum mechanics to molecules, we're going to be assuming what's called using what's called the Born-Oppenheimer Approximation. And the idea behind this approximation is you're going to treat electronic motion separately from the motion of the nuclei. And the justification for this is that the electrons are so small and they move so much faster than the nuclei that they can make instantaneous adjustments every time the nuclei move. Okay, so for practical purposes, then we can say it's as if the nuclei don't really care where the electrons are at any given location. Okay, at any given relative coordinate, the force that the nuclei would experience will only depend on where the other nucleus is. All the electrons will exert the same force at that particular location. There's an effective average force that will remain constant. Basically, you just smear out the electrons. So you think about the nuclei as just moving through a force field where the net force due to the electrons at any given relative coordinate is constant. So if the potential energy then would just as a function of the distance will only be depending on the distance between the two nuclei. Okay, R is the distance between the two nuclei. And when we're dealing with cases where we're as close as possible to the ground state, you can approximate the potential energy, which we usually represent by the letter U, as 1/2 kr squared. So that's similar to 1/2 kx squared. So we have what's called a harmonic potential. Okay, so the harmonic oscillator is a good approximation for describing the vibration of a diatomic molecule when you're near the lowest possible energy state. So the RRHO approximation, this is rigid rotor harmonic oscillator approximation. We can use that to model the energies of a diatomic molecule. So we say the total energy is whatever the translational energy is, plus energy due to vibration is essentially, what's this formula? The energy of a harmonic oscillator. So imagine the two nuclei as behaving like a two-particle harmonic oscillator. And then B, J plus 1, what's that? That's the rotational energy of a rigid rotor. Okay? So when we get to the lab, we'll be able to get values for these, the vibrational frequency and the rotational constant. And one bit of information we can get from our experiment is this B right here. Remember, this is h bar squared over 2 mu r squared, right? Mu r squared is your moment of inertia. From our microwave spectrum, we'll be able to calculate R, and that's going to be the bond length of our diatomic molecule. And that's the kind of information you'll be able to get from a microwave spectrum of a diatomic molecule, the bond length. Okay, this R right here, the distance between the two nuclei.